One of the geometric applications of the derivative is in finding the equations of the tangent and normal to a curve. So in this lesson, we have to recall our lessons or the concepts in analytic geometry. So we recall. First is the slope. So remember that we use the variable m to represent the slope of the line. And this slope can be solved by dividing the rise by the run. Remember that for a line, we only need 2 points to be able to sketch the graph. So for example, this here is point 1, or let's say that that is point P here, or let's just use P sub 1, and this here is P sub 2. So for us to draw a line, all we need to do is to connect the 2 points. We now have a straight line. So if the coordinates of point 1 are x sub 1, y sub 1, and the coordinates of point 2 are x sub 2, y sub 2, then the slope of this line, m, is equal to the rise. So this here is the vertical, no? That's the rise or the vertical distance between point 1 and point 2. And the run is the horizontal distance between point 1 and point 2. So these two are perpendicular to each other, meaning they form a 90-degree angle with each other. So the rise is the difference between the abscissa, or the ordinate rather, of point 2 minus the ordinate of point 1 divided by the abscissa of point 2 minus the abscissa of point 1. That's how we find the slope of the line. But if we are given the angle of inclination is actually the angle formed by this line with the horizontal. So this angle of inclination is represented using the variable alpha. So if we just look at this right triangle right here, if this is the angle, this is the opposite side, and this is the adjacent side, and the trigonometric function that we can use for the relationship of the three is tangent. So tangent of the angle alpha is equal to the opposite side rise divided by the adjacent side run. And this rise over run is again the slope, so meaning the slope can also be solved using the angle of inclination alpha. So m equals tangent alpha. So if we're given the angle of inclination of a line, then we can determine what the position of the line is. So once we have the slope of the line, we can solve for the equation of the line using the point slope form of the line. Okay, point slope form, which is given by y minus y sub 1 equals m times x minus x sub 1, wherein x sub 1, y sub 1 are the coordinates of a given point where the line touches or passes through, and m is the slope of the line. So from this point slope form, we can derive the general equation of the line, and that general equation is given by ax plus by plus c equals 0. So for us to find the equation of the tangent or a normal to a curve, we always represent it, or we always write it in the general form. And we can check if our answer is correct, because from this general equation, which we can actually determine the slope of the line by simply dividing. So the slope of the line is simply equal to the negative of the coefficient a divided by b. So through this, if this slope will give us this slope, then meaning the derived equation is correct. Okay, so how do we now use the concept of derivatives to find this equation. So the concept of derivatives is actually used here in finding the slope of the tangent and the normal to a curve. So let's start with the tangent line. So if we are given, okay, supposing this is, okay, this curve right here is y equals f of x. And we have the points P here. Okay, point P right there has coordinates xy. And we have another point here, Q. If x right here, if xy right here are the horizontal distance of point P from the y-axis and the vertical distance of point P from the x-axis, okay, that is, let's extend this. This is y, and this is x, because this is the y-axis, and this is the x-axis. Now, the horizontal distance between point Q and point P is the change in x. We're going to represent that using the change in x. And the vertical distance between point Q and point P is delta y. Now remember that this y right here is actually f of x, right? It's a function of x. Therefore, the coordinates of point Q, this is the abscissa of point Q, that's x plus delta x. And the ordinate of point Q is this one, y plus delta y. If y here is a function of x, meaning the ordinate here in point Q is a function of x plus delta x. This is a function of x plus delta x. If we connect points P and Q, there are 2 points right there. If we connect the 2 points, we are able to draw a line, because this line passes through a curve at 2 points. Remember that our curve right here is this y equals f of x, and this line passes through the curve at 2 points. Then we call this line as a secant line. Again, this is a secant line, wherein the slope of the secant line can be solved by dividing delta y divided by delta x. Okay? Or that's using the formula, the slope of the secant line is equal to the ordinate of point Q, which is f of x plus delta x, minus the ordinate of point P, which is f of x, divided by the abscissa of point Q, x plus delta x, minus the abscissa of point P, which is x. So simplifying, the slope of the secant line is equal to f of x plus delta x minus f of x divided by delta x. Or in simpler terms, we can see that it's a rise over run. So that's just equal to delta y divided by delta x. That is the slope of the secant line. Now, if we are going to move Q to make it closer to P, meaning if this goes closer to P, delta x becomes smaller. Okay? And this secant line will eventually keep on going nearer to the x-axis. So it approaches a horizontal line. But the limiting position would only be if a line only touches point P. If the line touches point P only, how would it look like? It would now look like this line right here. This line intersects the curve at a single point only here, only at point P. This line which touches the curve at a single point is what we call as a tangent line. So for us, again, if you want this Q to go closer to P so that delta x approaches 0, the limiting position of the secant line is the tangent line. So the slope of the secant line will approach that of the tangent line. If we are going to use the formula rise over run to find the slope of the tangent line, basing on this, we cannot solve it because it only touches a single point. We don't have 2 points. We need 2 points to use the formula y sub 2 minus y sub 1 over x sub 2 minus x sub 2 minus x sub 1. But since we know that the limiting position of the secant line is that of the tangent line, therefore the slope of the tangent line is just actually equal to the limit of the slope of the secant line when delta x approaches 0, or that is the limit of delta y over delta x as delta x approaches 0. We can see here that delta x would just be approaching 0 because this denominator right here cannot be 0. Because if this is 0, this would be undefined. This limit of delta y over delta x as delta x approaches 0 is the derivative of the function. Therefore, the slope of the tangent line is just equal to the derivative of the function y with respect to x at the point xy. Okay? At the point xy. Okay, this is one of the geometric application of the derivative of a function. So once we have the slope of the tangent line, we can also solve for the slope of the normal line and the equation of the tangent and the normal. Now, what is a normal line? So the normal line is just a line also that is passing through this point P. Remember, if this is our curve right here, the tangent line intersects the curve at a single point. This point where the tangent line touches the curve is what we call as the point of tangency. So the normal line touches also the point of tangency, touches the curve at the point, or intersects the curve at the point of tangency. But what makes it special is that it is perpendicular to the tangent line. Therefore, our perpendicular line is this line right here. This is the normal line. And normal line will always form a 90-degree angle with the tangent line. We also have a 90-degree angle, and it always touches the point of tangency. Because they are perpendicular to each other, the slope of the normal line is just the negative reciprocal of the slope of the tangent line. So once you have the slope of the normal and the tangent, you can go back to using the standard form of a line or the point slope form of the line to solve for the equation of the tangent line and the normal line. So for example, we want to find, we are to find the equation of the tangent and the normal to the curve y equals x cubed at the point 2, 8. So first thing that we need to do, again, we know that the derivative at a certain point or at a certain value of x is the slope of the tangent line. So what we're going to do first is to find the derivative. So differentiating dy dx is equal to 3x squared. After that, we can solve for the slope of the tangent line by substituting the value of x, so 3 times 2 quantity squared, so the slope of the tangent line is equal to 12. And since we are also looking for the slope of the normal line, we know that the slope of the normal line is the negative reciprocal of the slope of the tangent line, so we just write negative first, and then 1 divided by the slope of the tangent line, which is 12. After which, we're going to use the point slope form. So y minus y sub 1 equals the slope of the tangent line times x minus x sub 1. So same here for the normal line, y minus y sub 1. The only difference is this time we're going to use the slope of the normal line times x minus x sub 1. So since we are given the point 2, 8 here, we can substitute these values to x sub 1 and y sub 1. So y minus 8 equals the slope 12 times x minus 2. So simplifying, that's 12x minus 24. That's equal to y minus 8. The general equation of the line, therefore, is 12x minus y minus 16 equals 0. This is now the equation of the tangent line. On the other hand, we have y minus 8. Again, the only difference is the slope. That's negative 1 over 12 times x minus 2. So what we're going to do here is to multiply 12 here on the left side and distribute negative 1 here. So that's 12y minus 12 times 8 is 96 equals negative x plus 2. And simplifying, we have the equation, general equation of the line x plus 12y minus 98 equals 0. This is the equation of the normal line. Okay, another example. We want to find the equations of the tangent and normal to the curve y equals x square root of x minus 1 at x equals 5. Okay, so we're only given here the value of x, and we are given the function y equals x square root of x minus 1. So what we can do here is to, differentiate first. So because it's a product of x and x minus square root of x minus 1, so we are going to use the product rule. So differentiating dy dx is equal to copy the first term, multiply it to the derivative of the second term, that's 1 over 2 square root of x minus 1 plus square root of x minus 1. So our derivative is x divided by 2 square root of x minus 1 plus the square root of x minus 1. That's our dy dx. So therefore, the slope of the tangent line is equal to, substitute x here in these values right here. So 5 divided by 2 square root of 5 minus 1 plus the square root of 5 minus 1. So this is 5 divided by 5 minus 1 is 4, extracting the square root of 4. That is 2 times 2, that is 5 over 4, plus, again, the square root of 5 minus 1, this is 4, and so this is 2. So adding the 2, the slope of the tangent line, therefore, is equal to 13 over 4. That's 4 times 2 is 8, plus 5, that's 13 over 4. And therefore, the slope of the normal line is the negative reciprocal. So that's negative 1, you always start with negative 1, divided by the slope of the tangent line, 13 over 4, meaning that's equal to negative 4 over 13. So you just interchange the numerator and the denominator. So once you have that, once you have the slope, earlier we directly used the standard form of the line. However, we only have x here, so we need to solve for the value of y. So solving for y is equal to 5 because we already have the value of x. So if x is equal to 5, what would be the value of y? So 5 square root of 5 minus 1. Again, 5 minus 1 is 4, square root of 4 is 2 times 5, y is equal to 10. Meaning the tangent line will pass through the point with the abscissa 5 and the ordinate 10. So we now have the point and we now have the slopes of the tangent and the normal. We can now solve for the equation. So y minus y sub 1 equals the slope of the tangent line times x minus x sub 1. So y minus our ordinate is 10 equals 13 divided by 4 times x minus 5. Okay, our point was 5, 10. So we're going to cross multiply. So 4y minus 40 equals 13x minus 65. Simplifying, we have 13x minus 4y minus 15 equals 0. So when we transfer this to the other side, that would be plus 40. 25 rather. So this is the equation of our tangent line. And for the normal line, y minus y sub 1 equals the slope of the normal line times x minus x sub 1. So substituting, this is y minus 10 equals negative 4 divided by 13 times x minus 5. So we are going to multiply 13 here and distribute 4 here. So you have 13y minus 130 is equal to negative 4x plus 20. Simplifying, we have 4x plus 13y minus 150 equals 0. So this is the equation of our normal line. So if you're only given the value of x, you still need to solve for the value of y. substitute it to the given function. After that, you can now have the point, and you already have your tangent and then your normal. Then you can solve for the equation of the tangent normal using the point slope form of the line. Okay, let's have another problem. Find the tangent to x squared plus y squared equals 5 and parallel to the line 2x minus y equals 4. So in this problem, we are given an implicit function, and it's saying that the tangent line is parallel to the line 2x minus y equals 4. For this line right here, 2x minus y minus 4, okay, that is 2x minus y minus 4 equals 0. That is in the form ax plus by plus c equals 0. And remember that the slope can be determined by negative a over b. In this case, the value of a is 2 and the value of b is negative 1. So, therefore, its slope is negative 2 divided by negative 1, so the slope of the line is 2. It's positive, it is inclined to the right. So, since the slope of 2x minus y equals 4 is positive 2, and the tangent line is parallel to this line, if they are parallel, they have the same slope. Therefore, the slope of the tangent line is equal to 2. So, we can now differentiate. So, remember that we are looking for the equation of the tangent line. We don't have to be able to find the equation. We need the slope and we need the coordinates, but we don't have the coordinates. We just need the slope. So we're gonna we just have the slope, so we are going to use this slope to find the values, or the coordinates of the point, using also this equation. So given x squared plus y squared equals 5, we can differentiate that. So x squared plus y squared equals 5. Performing implicit differentiation, that we have 2x plus 2y, y prime, equals 0. Y prime therefore is equal to negative x over y. And since we know that the slope of the tangent line is equal to 2, then 2 is equal to negative x over y. We are given the relationship that y is equal to negative x over 2. Or you can use x equals negative 2y, either way. So what do we do with this? We are going to substitute this, either this to the given equation or this to the given equation, to solve for one of the values and then solve the other value after that. Okay, so let's use x equals negative 2y. So substituting that to x squared plus y squared equals 5, since x is equal to negative 2y, so negative 2y quantity squared plus y squared equals 5. Raising to the power of 2 for y squared plus y squared equals 5. 5y squared equals 5. Y squared therefore is equal to 1. So y is equal to plus minus 1. When we extract the square root, there always has two roots. There are always two roots. Okay? So, because we already have the value of y, we can now solve for the value of x using the formula. So, x equals negative 2y. So, at y equals negative 1, x equals negative 2 times negative 1, then we have positive 2. So we have 1 point right here, p sub 1, is equal to 2, negative 1. But if y is equal to positive 1, x is equal to negative 2 times 1, that is equal to negative 2. So we have another point here, p sub 2, which is equal to negative 2, 1. So which of these two will be the point that would give us a slope of positive 2? So let's try to see. This equation right here is actually a circle whose center is on the origin, whose radius is square root of 5. If the slope is positive 2, it must be inclined to the right. Okay? So if the point is at 2, negative 1, let's try to draw that. If this is our circle, okay, and the point is at 2, negative 1, let's say that's here. You have 2, negative 1, and we have the other point, negative 2, 1. Okay, so meaning there are two tangent lines that would give us a positive 2 slope. So it's either the line is in this position, and it could also be in this position. They have the same positive 2 slope, intersecting only the curve at the point or at a single point. Okay, so the slope is positive 2 at when it is passing through negative 2, 1, and the slope is positive 2, then our equation y minus y sub 1, which is 1, equals 2 times x minus negative 2, so that's x plus 2. Simplifying, y minus 1 equals 2x plus 4. Therefore, the general equation is 2x minus y plus 5 equals 0. Okay, that is the first tangent line. Tangent 1. But if we're talking about the line at 2, negative 1, passing through 2, negative 1, again the slope is still positive 2, then that's y plus 1 equals 2 times x minus 2. So 2x minus 4, y plus 1. So the general equation is 2x minus y minus 5 equals 0.